All right, everyone. Hi. I'm German, so I like to start on time, so we can check the first cliche. Welcome to the Whirlwind tour through the HTTP2 spec. This is a thing I have to pronounce quite often yet, so better get used to my weird pronunciation on that. I'm not a native. Okay, so it's labeled Whirlwind tour. I try to make it Whirlwind as good as it's possible in 60 minutes. So it's not that whirl, but kind of wind. Before we start, I'd actually like to know who of you already uses HTTP2 in production. Hands up. 1, 2, 3. All right, that's awesome. Appreciate that a lot. For the other ones, also for the ones who are using it actually, I hope I have tons of stuff new for you and actually to get a good look behind the scenes. Whenever I'm talking about HTTP2 and giving this talk, there are a few questions that pop up quite frequently. So I want to get these out of our way so we can do the deep dive in the spec, right? So let's start with that. I'd like to make a little quiz, so let's see. Hands up if you think yes. Is HTTP2 really done? 4, 5. Wow. Yes, it is, since a year. Is SSL mandatory? Hands up if you think yes. That's around a quarter. That's wrong. It's not. But all implementations you will see in the wild are only working with HTTPS. So the spec supports both ways, doing it encrypted and not encrypted, but every browser implementation and also the big servers only support the SSL version. So it's kind of right. Is it made by Google? Half one, yeah. No, it's not. What's speedy? That might be the obvious next question, right? It's a different protocol. It's something like legally or like from the specs and from the RFC perspective, it's something completely different from the contents. We will discuss this later, but it's similar. Is HTTP plain text? What do you think? Hands up. No one. Great. It's not. It's binary. Are headers compressed? Hands up if you think headers are compressed. Yeah, half the audience. That's true. Headers are compressed, and I will also talk how the compression actually works. My favorite question: will HTTP 1.1 still work? What do you think? Oh, come on! Obviously, browsers still support HTTP 1.0, and we will never drop the support for that because it would completely break the web. So if you deploy your web server, make sure it supports like all versions of that. Great. So that we get this out of our way, I like to talk a little bit of history. And this is important because you have to understand what's wrong with HTTP and why it is that way in order to understand why the new version is cool. So you first have to understand why it sucks, and then to see why the new one is good. So let's start. In 1989, Sir Tim Berners-Lee imagined his idea of the World Wide Web. It's browsers acting as editors, connecting all the different universities and research facilities to edit, collaborate, and create research documents. That was the idea. Browsers in the initial draft should act as editors. This idea somehow got lost on the way. In 1991, the first version of HTTP 0.9 was released and documented. Moving along, in 1992, there was actually the first draft for version 1.0. 4 years later, they published it as RFC 1945. Just 1 year later, they figured it was shit, so they released 1.1. So 1 has some obvious flaws. You can read about it on Wikipedia. I won't go deep into detail in that. But 1.1 was released 1997 under RFC 2068. And then in 1998, there was RFC 2326. Who of you know what that does? What this specifies? Anyone? It was released April 1st. It is actually the RFC specifying how interconnected machines should interact with each other for making coffee. And the HTTP protocol obviously cannot make coffee, so it should respond with 418, I'm a teapot. Okay, that was specified in this RFC. Let's move along. Okay, in 1999, RFC 2616 were completely replacing the old specification. That was because the old specification was kind of not clear in the way it was written down. The actual implementation didn't change, and the actual way how it behaved didn't change. But the way how it was written down and how the RFC was structured changed. So it made the old one complete obsolete. Then lots of stuff happened. Lots of little RFCs got released, I guess around 1 million about caching, all in this episode, in this time frame. And then in 2007, the IFT forms the HTTP BIS working group. And as far as Google told me, BIS is a Latin word for two. And their job was to consolidate all the RFCs flowing around regarding this 1.1 protocol. And you will see in a bit what the result of that was. In early 2012, the IFT also put out the call for proposals for HTTP2. And in November that year, Google handed in the SPDY protocol as kind of a base draft to iterate over to actually create HTTP2. So here you see how it is related, right? SPDY is the base HTTP2 like came out of. It's like the successor of that. And when we move on, in 2014, there was the actual result of the HTTP working group. They made all the RFCs regarding HTTP 1.1 obsolete and released 6 new ones. And the complete HTTP 1.1 documentation or specification is in these 6 documents. So it's consolidated all the other ones. This was a pretty important step, especially if you want to implement these kind of browsers, this servers or browsers, because all the RFC was so scattered and some were even outdated. So in May last year, which is 10 months ago now, HTTP2 was released under RFC 7540. I'm dropping all these RFC numbers because I personally find it pretty interesting to read through these, but we don't have lots of text on the slides, so if you want to read them yourself, I can really recommend checking them out. It's pretty interesting. So at the end of 2015, so the end of last year, 22% of all internet traffic was already HTTP2. I think this is quite an impressive number, right? And due to the fact that HTTP2 only works under SSL in the wild, like in the actual implementations, it makes sense to compare the number of HTTP2 traffic to the encrypted traffic of the web. And if we do this comparison, HTTP2 already has 35% of the whole HTTPS traffic. That's over 1/3. That's pretty great, I think. I hope that's not the fire alarm. I know it's blinking really weird behind that. But we'll move on unless someone walks in and screams. Burning. Okay. So that was kind of the history. And now to get us all on the same start, I also like to talk really quick about the HTTP2 basics. First of all, HTTP is plain text. So I can just spin up my telnet, my terminal here, and do a little telnet demo. So I can just open up a TCP connection to the Google server on port 80, and then I can just type in the protocol, right, in plain text. So I start with the status line, then the host, which is necessary, and then new line, and this actually makes the Google server respond. I think that's pretty cool. I hope you can see enough of that to actually make sense of that. This will not be possible with HTTP2 anymore. So you can't really like tinker around with that. You need to have special tools. It's stateless. You probably all know that. And this statelessness makes it super flexible. And we use it for everything, right? We use it for uploads, we use it for downloads, we use it for streaming, we use it for APIs, and not only documents, right? It was intended to only serve documents. Even the idea of having assets was not in the first spec. But due to the fact that it was so flexible, we could do so many things with that. And if you see how much it is used, it's kind of the protocol of the web, right? So it's really a thing used very often. But this also brought in some problems, right? Due to the fact it was not invented to serve all these purposes, and the web was not invented in that way, HTTP2, HTTP 1.1, which is almost 8 years old, no, 18 years old. The web matured since then, right? In the last 18 years, the web has evolved pretty much. And here I have a graph graphing the last 5 years, the total request size and the total transfer size, and both numbers doubled, right? And just in the last 5 years. And I think this graph will even continue. The average website has 38 connections, different TCP connections, to load one website. This is a huge number, and this brings a lot of problems. And I think the biggest problem is what I call request bonanza. This is not the official word for that, so don't Google for that. I don't know what the results would be, but it's probably not the problem I'm talking about here. But what I mean is probably the thing you all know about. So you have the browser here on your left and the server on the right. And if the browser is going to fetch an asset, in our example, it's the index HTML, the server responds, and then in the index HTML, you will find another asset. So parsing that, you will find another asset, then you fetch this asset, and while parsing this asset, you will find even more assets, right? And you all do it back and forth. So there's no real deal to fetch things in parallel. We'll talk about this in a second. All this adds a ton of latency, right? In all the recent years, we have optimized for throughput, and while that, ignoring latency, right? We all like concatenating assets, which is great for having a good throughput, but due to the rise of mobile, we really see all the problems because the throughput with 4G is pretty good, right? But the latency is still shit. So when you load a lot of assets on different TCP connections, you always have this overhead of establishing a connection, making the handshake if it's encrypted. And how does it look like in the wild? Well, I have an example here. So this is the Verge. I don't read that, but it's apparently a good example, and you will see in a second why. So I will just load the Verge in my browser, and we'll watch the network tab to see what's actually going on here. So I have a little video here. And let's fire it up. And we see the first initial request already takes some time here. Then you see some more assets, whatever. This is real time, by the way, right? So I'm still waiting for the website. So I have typed it already, hit enter, but nothing. Wow, it's loaded. And nobody can read this, but trust me, it's 12 seconds. So loading the Verge to the load event takes 12 seconds. And I didn't cut my connection there. It's just what I have at home, and it's not like too bad of a connection. I'm living in a bigger city. I have 50 MB sync. Not sync, but it should be, right? It's just a regular thing. And it shouldn't take 12 seconds to load an average website, I think. What I found even more interesting is that it's not only 12 seconds, it is the whole website is 1.5 megabytes. So while I'm here, I'm surfing on a roaming plan and I have 50 megabytes included. So I cannot even load this page 50 times unless my data plan is exhausted. And also, this page takes 170 requests to load completely. 170, imagine that. Not over all the different hosts, but I think this points out all the problems we actually have in the web, performance-wise. So, in order to do a deeper introspection to that, the same video, but just slowed it down a little bit so we can better see what's going on here. So there you see the initial request. Here you see that it starts downloading resources at the same time. So it started at the same time, but look at how this pattern looks like, right? This is important. What we also see here, what I think is pretty interesting, we have this wonderful waterfall, right? To really see that another resource triggers another resource, triggers another resource. Again, same numbers, just a bit more of loading time. You'll see all different. You'll even see here, for example, this is an HTTP2 request. So I think some of these advertisement networks are already upgraded. But most of the stuff is 1.1. All right. I got mad, so I did what I always do when I got mad. I'm on Twitter. And it's not something against The Verge in particular, right? I mean, if you just load your company's website, take a look at the stats and see how bad you are. My company is pretty bad at this as well, so I don't want to blame only third parties. Then let's take a look at the pattern I just pointed out. When I say it's not possible to fetch requests in parallel, your first idea might, Ole, you're wrong. Actually, you can transfer multiple resources on the same connection. It's called connection sharing, but this thing suffers from a huge problem. So this is what the browser does, right? So the browser fetches or asks for 3 different resources. So in our case, it's the index.html, the feature CSS, and the annoying JavaScript. But HTTP 1.1 has one huge problem. The response has no identifiers. So the server must respond in the same order the resources were requested. And if you think of your average PHP file or your PHP server, this file is the one that takes the longest, right? Because the other one is static. So the browser the server is not able to answer the requests. It actually could at this moment in time, but rather it has to wait until the site is generated that the client can make the mapping. So it knows this is request, this is the asset I requested first, so the first answer I get is probably that asset. So let's recap here on the whole blocking. Well, it's the order matters, right? So the order in which your request appears is important. The slowest request blocks. There are no workarounds, which I think is particularly interesting because it's just a limitation of the protocol, and this is one of the reasons why HTTP2 was designed the way it is. And therefore, it's often unused. Most browsers just turn it off, right? But as developers, we really endeavored, right? We really tried to work around these issues. And as, humans, we try to use the way of the least defense. So rather than just opening up the big bottle and figuring out the protocol and how we can improve the web as a general, we just improved our project. So we came up with the idea of spriting, right? Putting all the different images in one huge image and just positioning it with CSS. Huge bullshit, or not real bullshit, but huge overhead if you just want to update one image and then you try to build tooling around that and add a lot of complexity, right? Just to solve the one problem. Concatenating, one of my favorites. Dumping all your string-based assets below each other and hope nothing breaks. Domain sharding, this is particularly worse when you upgrade to HTTP2. We'll see later why. But this just means that you serve assets from different domains in order to work around the limitation that there can only be five requests in parallel to one domain. Also, lots of stuff got inlined based on the size, so this also adds a lot of complexity to the project. And I've seen the weirdest preloading hacks, right? My company is the best example for that. What we do is on every landing page, so whenever you type in jimdo.com and come to any landing page, we will load the complete application JavaScript and CSS, just that your browser have it in the cache. This violates so many software architecture rules that it's really hard to deal with. But this is just what many people do, and this is just the way of least defense. There are also cookie-free domains, and I have this little asterisk here because it is a great idea, and please keep on doing this even in the newer protocol versions. So in general, we try to save all the different requests, right? So now we have talked about what's the actual problem with the protocol we are using at the moment. But I also want to bring in the solution to this, right? And how this can be fixed right now, because the tools are there, as I mentioned at the beginning. So let's take a look at HTTP2. First of all, HTTP2 is compatible, so it's not breaking the web. The scheme will stay. No user will ever see an HTTP2 in the browser bar, and the whole semantics stay. So we will keep continuing having requests. We'll keep continuing having responses, headers, methods. All this stuff stays the same, but all the this is the layer we're operating on, and which will be the same. But all the underlying stuff completely changed. I will discuss this in detail in a second. First, let's have a look on how upgrade looks like. Upgrading from HTTP 1.1 to 2. First, let's take a look at the specs. So this is a very theoretical thing because you will never see it in the wild. So on the non-encrypted connection, it will just use an upgrade header. So here you see a request. So it's doing the get, the host, the connection, and then the upgrade header. It tells to which protocol the client wants to upgrade. Then it also sends the H2 settings, and you will see in a second why this is important here. So the server sees this request, and what the server, if it's supporting the H2C protocol, will respond with an HTTP 101 switching protocols, tell to which protocol is going to upgrade, and then new line, and directly start with binary traffic. And this is why, even in the request, the client has to send the settings, because the client has to specify the kind of the boundaries they're acting on the protocol. For example, max package size, concurrent streams, and this kind of stuff. And in order to avoid this back and forth loop, the client is always sending out this one. And because this would add up so much more traffic on the web, this is one reason why they dropped the idea of doing this in the wild. Then there's the connection upgrade on a secured connection. This will be a lot of acronyms in here, but bear with me for a second. Upgrading HV1122 on a TLS connection is done by ALPN. ALPN is specified in RFC 7301, and actually ALPN is not the complete acronym, actually it's TLS ALPN. So it's the Transport Layer Security Application Layer Protocol Negotiation Protocol. If this makes any sense. To make this even more confusing, ALPN is based on NPM, which was invented by Google for Speedy. Anyway, how does it look like on the protocol? So this is the SSL handshake, and this is the part which is interesting for us, because when you have the TLS extension called ALPN, the client offers a set of protocols it supports, and the server can just pick one. That's how they negotiate on the protocol. Pretty easy. Then there's all this handshake security stuff. Little heads up here. You've seen H2 and H2C, and unless in the 1.1 protocol, the longer version here is the non-encrypted. So H2C is clear text, and H2 is the encrypted one. Why is it? I think the reason is pretty funny, because the string H2C is reserved in the ALPN identifier space. But it describes a protocol that does not even use TLS. So there are like two weird things. And the first, why should the string for the clear text version be in the protocol spec for the encrypted version? And then why is there something in the identifier space which is not used by it? So they're definitely lacking garbage collection here. HTTP2 is multiplexed. It's using streams, and this is the one feature to actually work around all the limitation we just discussed. It can transfer multiple resources on a single connection. So on a single TCP connection we have here, this is one physical TCP connection, as far as it gets physical. And there are logically streams on that, and the streams contains of frames. If you look at the data transferred, it's just frames transferred on one connection, but a frame always belongs to a stream. So thinking of that in this model makes way more sense, because there can't be any frame not belonging to a stream. And a stream or a frame can be anything. We'll take a look deeper on this in a second. And a stream is always one request-response cycle. It can be, a stream can exist without having request-response, but there cannot be any request-response without a stream, and there cannot be two request responses on one stream. So let's take a deeper look at the frames. Frames are binary, and now the first spec part comes. This is the actual frame layout. Let's have a look how this looks like. That's the binary frame, and it starts out with a length. Then there's the type of 8-bit. Then there are the flags, a reserved bit, and then there's the stream identifier of 31-bit. And then there's the actual frame payload. So this is kind of a generic frame header for all the frames we will see in a second. So when I was reading through the spec, I actually found that one. And in the specs it said, this bit has always to be 0, ignore it. And I was like, what? Why it's even in there then? And it's not mentioned in the docs why it is in there, right? It's just say it is 0, ignore it. And there's no additional reasoning. I got really curious, so I went out and asked the authors of the spec. And it turns out it's for platforms who does not support unsigned integers. So they can just use signed integers and do whatever with this bit. Well, OK, so we can support this platform. Great. Now let's take a look at the different types of frames we have. The first one, and that's the one you will see most of the time in production, in the real world, that's a data frame. It actually carries all kind of data. It can be an asset, it can be HTML, it can be whatever. It's just binary data. And this actually consists of the pad length. This specifies the padding you see here, and then the actual data. Padding is a security feature because TLS on SSL protects the content itself, but it is really bad at protecting the length of the content. So attackers can guess the length of your content, and this is an attack vector, and this is why they added the padding.
Just a quick question about the padding. Is that the content itself, is it randomized or is it padded with zeros? Do you know?
I don't know that. Sorry. But check out the specs. They're pretty comprehensive on that. So there are huge sections about protocol security. And then there's the priority frame, which is type 0x2. It has the stream dependency and the weight. So HTTP2 uses weighted dependencies. And I will have a section later on this, how this actually works in detail. Then there's the reset stream frame. This indicates an error on one stream. So when there's a parsing error on one side, the other side can just close that one particular stream while keeping up the connection. Then there's a settings frame. Settings belong to the complete connection. And these are, for example, how many streams there can be in parallel, what's the max size for data packages, and this kind of stuff. And it's always key value. There are also a bunch more. And we'll go through a few more in this talk, but for the rest, check out the specs. I think I have covered the most interesting here. Here I have an actual implementation example. So this is a ping package, type 0x6, with the acknowledgement flag. So the acknowledgement flag is that the receiver should actually send back a ping frame, hopefully without the acknowledgement flag, because it would go ping pong then. So what do we have here? First, there's the length, and the spec says that the ping package has to be 64-bit length. The length is just for the content, so it's not for the headers. Then there's this type. Type is specified by the spec. It's 0x6. Then there's the flag. The flags are also specified per frame in the specs. So the ACK flag is 0x1. Then there's the 1 bit. We're always ignoring. And then there's the stream ID. What I particularly like and want to point out here is that when I see the stream ID, I can tell that this one is from the server, because clients use odd numbers and server uses even. This way, they avoid any collisions on the IDs. And I think this is pretty cool. So everyone can just take their own stream IDs, and they will never collide. And then there's 64-bit of opaque data specified in the protocol. So with this at hand, you can implement what you have already in your web server, right? And you would solve most of the problems we have, like head-of-line blocking, optimizing for latency, all this kind of stuff could be completely solved by the stuff we saw. But this is just half of the spec, because the authors said, when we're doing a new version anyway, let's really improve the web. So there are a few things which are not in HTTP 1 yet. They're not around in the web yet. And I want to talk about this as well. The first one is a thing called server push. And server push is a feature which you can think of a direct connection from the server into the browser's cache, right? So what does it do? Imagine a client requests an index HTML. The server can tell, I know you're going to request the index HTML here, but I know that you're going to need this JavaScript and this CSS file as well. So without the client actually asking for it. This is, I think, one of the biggest changes and one of the things with the biggest impact in the whole protocol. And I think this can make the web enormously faster. There are no actual implementations or like generic implementations at hand yet, but I think this is pretty promising. You got the pun with promising? Okay, so this is the frame which actually initializes the push. It's pretty similar to the header frame because it basically is a header, but it's initialized by the server. So it has a pad length, the one reserved bit, then the soon-to-be stream ID. So this is a server stream ID. And then there's a header block fragment. I will talk about this in a second as well. And then there's the padding. So that's about server push. It also supports flow control. So client and server both can, while transmitting data, change the weight of assets. So while receiving that, they can change which asset is more important now. And my favorite example of this could be an image gallery. So imagine you have a long HTML page, and browsers could implement a way that they're not going to fetch the images which are not in the viewport yet. And as you scroll down, they can start fetching it. And if you jump, and they even have fetched some images, but they're out of the current viewport, they can still continue fetching the ones they don't need yet, but they can reprioritize the other ones. So they can change priorities. Both sides can change priorities while transmitting. They do this by weighted dependencies. And for me, this is always hard to reason about. So I also want to bring a little example here. This is done by a priority tree. This graphics I kind of rebuilt from a presentation from Moto Ichiba. I have the link on my slides you can find on Join In. And he has done a complete talk just about how this prioritization in HTTP2 works. It's pretty insightful, lots of details in there, and I loved it. So here we have one stream, stream ID0. This is always the initial stream. And this is the dependency. So stream ID3 depends on stream ID0. Here we have another stream, stream of 5. This is stream ID here in the middle, and this is the weight. And then we have another stream ID7 and stream ID9 here. So let's try to understand what's going on here. First, as I mentioned, at the very bottom, at the very top, there's stream ID0. That's the initial stream ID. It's always 0. And a default weight, so when there's no weight specified, is always 16. And stream ID3 should receive 2/3 of the available resources. So that you can see here and here. So that's 2/3. And stream ID7 should receive half of the resources of stream ID3. So they split, because they're both 16, all the resources. So it's going on 50-50, right? Even though it's not 50-50 here, but it's 50-50 here. So they split it up even more. That's very theoretical, and I want to bring an example how this actually looks like in Firefox, because that was the one example in the talk, and I want to just show it off. So imagine there is a request starting now, and I will have another example later on where you see the same pattern. What Firefox does is just opening up new streams. So it's building up this dependency tree. There's nothing transferred yet, right? So it's just building up this tree. And then it starts with the HTML document prioritized by the header frame. Then there are some CSS files. They go up here. Then there are some JavaScript files also in the head. Then the browser might find some images in the body, so they go below here. So same priority as the 13, or same dependency as the HTML document. And when the browser then also finds some JavaScript at the bottom, so maybe right before the body closing tag, this is what most of us do, right? They will go below stream ID5. Your most urgent question might be, why are they doing it this way? And the answer is, I don't know. But what I know is that this is the most efficient strategy compared across browsers. This is because Google's Chrome still has the strategy they used for Speedy, and this changed a lot. So what they do, I mean, it's not like super slow, and the difference is kind of really small, but this is the most efficient way of doing it. And what I also find pretty interesting is that the Internet Explorer, they just don't really use this. So every stream they open depends on 0. So it's a flat thing. But I mean, that's not a big thing, a big deal, right? I mean, it's totally okay. It will work, and it's just a It's just an option where they can gain some speed in the future. So now let's talk about the compressed headers. We were just talking about this at the beginning. So headers are compressed in the protocol, and this is how it looks like. So here's the headers frame. It's actually type 0x1. It starts with the pad length, the 0-bit, the stream dependency. So this new stream depends on. So a header frame always also opens up, or a push promise opens up a new stream. And then there's the wait, and there's the header block fragment, which is binary data, and then there's the padding. So how does this header block fragment look like? Well, the header block fragment is actually specified in another RFC. It's RFC 7541, and it's called HPAC. So HPAC is a more or less generic RFC, generic way to compress key value pairs from server to client. And it's actually, the technique it's using is, it consists of a static table and a dynamic table, and the encoder decides what's going in the dynamic table. So how does it look like here? We have an example. So this is request headers, even if it looks like est headers. We have the method get, we have the scheme HTTPS, we have the host gmail.com, path is resource, the user agent is Mozilla, and the custom header has some custom value. And this is static table. The static table is just part of the RFC, and you'll just, if you're implementing this, you will just like copy paste it from there and bring it into some kind of data structure. You can look it up. And I think this one is particularly interesting because method get might be one of the most sent headers in the web, right? Because this is what most of the stuff is doing on the web. And when I'm surfing with my browser on my one connection, my user agent probably won't change, and also the host won't change, right? So this is why this might change from user agent to user agent, and even like from different connections to connections, but it will stay on one connection. And here you see the one exception from the statelessness we mentioned. So the compression table, and especially the dynamic part, is stateful, but it belongs to one connection. So on one connection, there is state in the client and the server, right? So you have to keep the table, the connection table, to belonging to the actual socket if you're implementing a server. And how would the encoded headers look like? Well, so the request header method get, you can look it up here by index 2, would be just index 2 in the encoded headers. Then scheme HTTPS, something you will see pretty often, would be ID 7, and so on and so forth. This one is interesting because here we have index 19, which is not on here, but I'm pretty sure is path. And it doesn't have a value, like authority here, or referrer. And these strings are HUFFMAN encoded. I'll talk about HUFFMAN in a second. And the encoder decides if the server should add these values or the headers, like in this example, to the static table. Yeah, to the dynamic table, sorry. There's one other funny side note in here. Have you noticed something here? It's actually spelled wrong, and that's not me being stupid. This is how it is in the actual spec. And what I didn't know, maybe you know that before, is that it is wrong in the spec. There was a typo in the initial HTTP 1.1 spec. It has been like that forever. And if you check out the actual implementations, most of the server and client implementations supports both ways of writing it, right? The correct way and the wrong way. And in HTTP 2, they decided to not change it. So you'll still find this error, this typo in the HPAC spec. I think that's kind of funny. Well, let's take a look at HUFFMAN encoding. Who of you knows what HUFFMAN encoding is and how it works? Okay, that's about 5 hands. That's pretty good. So I want to try to explain it in 1 minute so that the 5 who just raised their hands won't get bored, but also that I can just bring you others on board. So HUFFMAN encoding 1 minute. We want to encode the string Mississippi River. And the idea of HUFFMAN encoding is actually that characters which occur often take the least space in the encoded value, right? So here the I and the S probably might be encoded pretty short. So Mississippi River has 17 characters, where each character is 8 bits, so this results in 136 bits. First thing you do if you want to encode it, you count the characters. So M1, I5, S4, and so on. Then you just order them by occurrence, or by how often they occur. So you have I5, S4, P2, and so on. So next thing you do, you start at the very lowest values, combine, like concatenate the characters, and sum up the numbers. So you would get E space 2. Next is MV2, PR4. So then we go over to MVE space 4, PRMVE space 8. Then there's IS9 and ISPRMVE space 17. So you see, we always get up to the 17 here again. Hopefully. If not, you made a mistake. Next thing you do is you walk down every branch combination you have. First you assign zeros to the left branch side and ones to the right-hand side. And then you walk down every possible combination you have, like here. So I is 0, 0, S is 0, 1, P is 1, 0, 0, and so on and so forth. And with that, you got your encoding table. So with that table, you can actually compress the string Mississippi River. The compression table has to go with the result in Huffman encoding to actually be able to encode it again. So the string itself is 64 bits plus the table. You will still save around 70% if you encode the string Mississippi River like that. So the Huffman encoding is a pretty good choice to do that. And what the HPAC spec also does, the HPAC specs come with a complete Huffman encoding table. So they analyzed a lot of traffic. I don't know the numbers, but I just was reading the spec this afternoon, and they have like 1 or 2 pages Huffman table, which you just copy over to implementation, and then you don't have to transfer the table, right? So the lookup can be done by this table, which is in the spec. And they created this table by analyzing a lot of headers in the web. I think this is particularly interesting. Well, now I want to take a look on how HTTP2 looks like in the real world, right? So first of all, it's already here, and we have a few minutes spare. So I really want to do a little demo here. So let's see if we can get this working. Ooh, my emails. You don't see them. That's good. All right, mirror. Now you can see my emails. Great. Oh, there you see my HPAC implementation. All right. Let's go over here. Whoops. This is always when I open up a new tab. It's an awesome feature of Michelle. It takes long, but it's worth it. All right. So what we're doing here, whoop, way too fast. So I use the tool ng-HTTP. I pass a few flags. V is verbose. N is, I guess it's discarding the actual downloaded content. And U is whatever, I forgot it. What's that? Ah, you can't see it. That is shit. Well, let's like that. No. Yeah, now, right? Okay, awesome. That's shit. Okay, I think it's going to work at this. Yeah. Actually, I don't know how to move it over, but oh, I can. Oh man. Okay, let's do it like that. I hope this. Awesome. Okay, let's do it like that. Okay, so we have a tool, ng-HTTP. We're passing a few flags, and I'm using the Golang implementation of the HTTP2 server because they have a pretty good implementation. They shipped it with 1.6, so they just released it. And they put up this version of the server to check their implementation, and that people implementing the protocol can also check against their implementation. And let's just fire it up and then analyze what's happening there. So first of all, it's just connected, and then they negotiate it to the protocol H2, which is the encrypted protocol via ALPN, right? Then the client is sending some settings. Let's take a look. It's max concurrent streams, so we can send 100 max concurrent streams and the initial window size. Then it's opening up some new frames, so stream 3, 5, 7, 9, 11, and 13. And then it's sending some headers, so the request headers. And what you see here is colon method get, path reg info, so just the same thing we just saw. And what I want to point out, because this might be kind of weird to you, is that there's this colon headers, right? And they're lower, downcased. in order to keep the semantics of the HTTP protocol, this information has to be preserved, right? Before that, it was part of the status line, so it has to be in every request. But now that it should stay there, they got injected into these column headers. So everything which was part of the status line is known as column headers. I don't have the hex dump version here, but we can check it in a sec as well. So then we receive some settings, and then there's an acknowledgement for the settings we just received. Then we receive the headers, so status 200, connection type, and then we're sending another acknowledgement for the settings. So as you see, it's all happening in parallel. So this receives settings ACK. So these parts belong together. But due to the fact that it's all happening in parallel, it can happen that the headers we received are already here and the request is almost over, but we still do the acknowledgement thing which is going on. Then we receive some data, and then we're sending the go away frame, which is actually closing a connection. Let's see if I can just call, right. So here I have the same thing, but just with a hex dump. This is the actual content. But what you see here is the actual headers. So these are the compressed headers. And if you want to, that's what I just mentioned. That's stuff I'm doing at the moment. So I want to write an implementation for that. So it's just copying over this hex dump. So the tool NGHTTP is pretty nifty, and I can really recommend using that. Wow. I have another thing I really like to show. You see my notes, right? No, you don't. That's good. My notes are my castle. Okay. You're allowed to see that. All right, this is the Golang implementation site. I was just querying from a console. And they have a demo called Goofer Tiles. What is Goofer Tiles? Let's just request the Goofer Tiles demo with 200 milliseconds latency, so I've got enough time to explain it. So the Goofer Tiles image is not one big image. It is lots of small images. And we're receiving in here tile by tile, and I'm just going to put it a bit more here. Is it big enough? Yeah, right? So if you receive it with 30 seconds, milliseconds latency on an HTTP 1.1 connection, this is how the image would build up. Again, 1.1 is optimized for throughput, not for latency. Now, if I do the same thing with HTTP 2 and also 30 milliseconds latency, the image will load like this. Because we have 30 milliseconds at the very beginning, and then all tiles got ascended at the same time, right? So I think in this demo, it makes a lot of sense. So with 200 milliseconds, you might see it a little bit better. And here, every tile has, again, because it's opening up a new connection, right? So it's waiting, again, 200 milliseconds for each tile. OK. I think that's now the demo. Right. There are tons of these demos around. You can check out in the ends of my slides. There's tons of links. But now let's take a look at the browsers actually supporting it. As you just saw, I was using Safari. So as you see, Safari is using it. And what do we do when we want to check if something is supported by current browsers? We go to Can I Use? And here you see every recent browser does support it. And if you check the number, I'm German, so I checked the number for Germany. In Germany, the support is 73%. And even global, it's over 60% support. So Can I Use has this nice feature that you can display by relative usage. And this looks like that. So due to the fact that 3 people raised their hand if they're actually using it, I might ask you, why are you optimizing for this? Right? Every other browser supports it. Right? If you see here, Firefox does it for a very long time. Chrome does it for almost every version. Here you see the Internet Explorer. This is version 11. So that's like that high. Whoa. OK. Here you see in the latest iOS release, and iOS had a great adoption rate. It's also supported. Same for the latest Safari release. It's also in there. The Windows has a little bit of a different color because it only works with Windows 10 for whatever reason. I don't know. Maybe they're too stupid to implement it correctly. Yeah, so my question is, why are you optimizing for this? And then let's talk about the servers, right? Because the web is made of clients and servers, and now that I really proved you that there is no reason to not use it on the client side, let's take a look at the servers. So in order to understand the impact of a browser supporting it, I think it's interesting to check the market share. So really rough numbers here, but I just looked them up on the internet. The Apache has almost 40% of market share on the web. The Microsoft IIS server is almost 30, Nginx almost 15. What I found particularly interesting is that the Google Web Server, which you cannot deploy on your own, already has 2% of the global traffic. Sick. And then there's any other web servers like, I don't know, self-written ones, Puma, application servers, all in the wild, I don't know, the rest. So Google Web Server, let's start with that because it's like the smallest number here. Nothing published, but we know that they dropped support for SPRITING February last year, so they probably had support for HTTP2 then. Apache has support since July last year, so version 2.4.12. And Nginx has support since July last year, September last year, which is version 1.9.5. And even IIS has support since Windows 10 and Windows Server 2016. So every recent server has support as well. And upgrading and using it is actually super easy. So let's take a look at Nginx and Apache, because that's what I guess most of you use in the PHP environment, right? So using it in Apache is actually one-line change. This is all you need. You just have to load the module. There's another prerequisite, as I mentioned. You have to use SSL already, because the implementation only works when SSL is enabled. So you just have to load the module, and that's it. This part is already optional. It's just about the logging. Now let's take a look at Nginx, and I really love the Nginx implementation. So this is the Nginx. This is the block you already have. Here you're listening on a certain port, and you just have to add that like 5 characters. That's it. It's a 5 characters change, right? So if you have a decent version of Nginx, just add this 5 characters, and then you enabled it, right? And with that enabled, you can do like craziest things, but I will talk about that in a second. Sorry to say that, but I think you're holding it wrong, because we are holding it wrong, but I'm standing here and you're standing there, so I just wanted to point it that way. I think we as developers are holding it wrong. We are not using the features like server push and flow control, and even though if you would upgrade the way I just showed, you would not use it as well, because in the actual implementation, there's no way to actually using it, because push and server push is actually something the application has to decide what to push and not the server. And there is no way from the application to talk to the web server. I mean, there is one, but it's not supporting HTTP2 and the idea of sending commands. Right? So there is FCGI, for example, but there's no idea how server push could be implemented. Same for flow control. Right? The server has somehow to decide itself if it wants to change it. But if you're writing any programming language, might it be PHP, Ruby, Elixir whatsoever, can't, unless you're writing the server at the moment, right, and interacting with the server directly, there's no way when you're on this abstraction layer of application servers and applications to communicate here. I think the solution for this is either we come up with a new kind of protocol for application servers and applications to do this, or to use this with actual network middlewares. So what about writing a proxy, a reverse proxy, who's just caching the index files and then build up a mapping of the actual page you requested and the assets in there? And when it sees the request, it just passes through the request, but sending out the assets needed. I think this could be working. I tried to implement this in Nginx and Lua when Nginx had the support, but I figured that the API is like poorly documented would be wrong because it's not documented. So it's not poor documented, it's not documented. Maybe this changed. It was in September last year. Maybe it's way better now, and you can just implement it with a few lines of code, I guess. So what I want you to take away from this talk is really optimize, like upgrade and then optimize. You should stop concatenating files, because this is just a workaround we did in 1.1, which is absolutely not feasible anymore in a world where you optimize for 2, right? And you all know the pain we have with concatenating. Imagine your JavaScript application, like your application.js, which is like about 1 megabyte files, and then there's one library which updated, and the thing you have to do is you have to send out again the whole JavaScript. there's no way, because it's just one blob, right? There's no differentiation between the files. And you could have this, right? You can just include all the JavaScript files, and you don't get a penalty for this anymore. So concatenating there's no reason to do that anymore. Same for spriting, right? It was the thing we had to do. We had to optimize for the 1.1 protocol, but it's not state of the art anymore. And this is the most important one, right? Stop domain sharding, because all the upsides I was just discussing are per connection. And if you shard it across domains, you will lose like all the upsides, because you will have shared header compression tables per connection. You can't do the rebalancing and the reprioritization of assets when they're on two different connections. So this is the most important one, stop domain sharding. And I want to propose to really trash the asset pipeline, because you don't need it anymore. This is obviously just the half-truth, and it's like with a big claim, because if you use CoffeeScript or something, yeah, browser don't support it, you have to compile it or transpile it. But all this stuff I mentioned before, like concatenating and this, it's just, you don't need it. Just throw it away and remove all the complexity, right? When you jump on, like if you ever deal with Webpack, it's like, oh shit. It's adding complexity where there's no need to have complexity anymore. So I want really to encourage you to start using HTTP2. Not only upgrading, but really make use of the features. Declutter your big JavaScript blob, stop spriting, this kind of stuff, and upgrade it, right? There's almost no good reason not to do it. We always optimize for the majority of our users, right? And check the user base. If you're supporting a website which has almost only IE8 users, well, then you should probably not upgrade, right? But this is hopefully nothing I have to tell you. Well, something I really want to do is to give my company a little shout out. So I have this 5 seconds of fireworks for them. They actually gave me the time to work on this, and they actually helped me coming here, preparing all this stuff. And if you want to know more about building websites with our awesome website builder, or working in Hamburg, the most wonderful city in Germany, please just come to me and ask me. And also, one other little detail is my name. So I'm Ole Michaelis. And if you got any feedback to me, please just tweet me. This is like the best way to approach me. Just jump on Twitter, follow me at CodeStars, drop me any line you have. Come here afterwards, after the talk. This is my GitHub. What I always want to point out, GitHub has this following feature, and I don't know if someone uses it, but I think that's bullshit. But if you want to, this is a thing you do, just follow me on GitHub. Check out my homepage, codestars.eu, my side projects, Lar.io, and So Coded, the awesome web conference in Hamburg. I have these stickers with me, so if you want to grab a sticker, just come here after this talk. And this is all I got. Thank you very much. We have, do you want to do questions?
I have a question.
Okay, yeah, there's a question, so let's see.
A couple of questions. One thing,
Let's just do one, there are other questions as well. So pick your top priority.
Okay, I'll pick the other one then. It was just the actual payload is gzip, right? That's true, isn't it? They use gzip compression on the payload in HTTP2. And with that being the case, would you then argue also to stop minifying as well, on the basis that there's no point if it's going to get compressed anyway? It's again just a bit of extra complexity that's not needed.
Right, that would be my recommendation. If you minify, you would gain some better results, because minifying also like shorts variable names and stuff. This is something gzip doesn't do. But in favor of like removing complexity, I would say yes, do it. But this is a decision everyone has to like do on their own. It's not something which is like special to the protocol. Okay, another question.
You mentioned domain sharding and what have you, but what about CDNs and things like that, where you do have connections to different providers for assets? Is it worth not doing that anymore and kind of bringing them under one server?
I think CDNs are great, and if you manage to get all your traffic through one CDN on one host, this is great, right? And then hope that your CDN provider implemented right. But they usually have one host, right? And they Just if they just manage to have it in one connection, that's completely fine.
Sure. Okay.
So I think the CDNs is like CDNs as CDNs are not a problem here, right? If they implement it poorly, that might be a problem. And I think CDN are a good solution to this whole upgrading problem in general, because not every web server, especially if you have application servers, so implemented in a language and not the generic ones like Nginx or Apache, CDNs are a good way to upgrade because they can give you all the upsides, right? They cache the actual assets and can deliver the assets for you because they have them in the cache. And your server, which is maybe just rendering HTML pages, then don't even need HTTP2, right? If it's a CDN, it has a good implementation, it can handle that for you. So it can handle the HTTP2 connection on the one hand and then just transform it. So transform the one to the two part. But this is always about the implementation. Yeah.
How practical and easy is it to arrange a fallback to HTTP 1.1 if the calling browser doesn't support that? Because the transparency of switching Apache is quite quick and easy. So the only question remaining would be, how easy is it to fall back for the older browsers, as it were?
There's almost no penalty. There's actually no penalty because when you the Apache has the LPN extension, and it doesn't it supports HTTP1 as well, right? So it's not only sending H2 as protocols, so it sends, I guess, HTTP1 and 2 and whatever it supports as well, and then the server just picks, right? So when the client supports it, that's totally fine. There's no
Thank you.
No penalty. Here in the front, there's a question. I think we just do two more questions. Then
let's say that you have one or more proxies in front of your web server. Which part of the chain has to implement that HTTP2 protocol? All of them?
The first one you hit.
Okay.
Because it's via TLS, so intermediaries don't see the traffic; they just see an encrypted blob of TCP. So the first one has to do the SSL termination and then handle all this.
Okay.
Yeah.
Thanks.
Last one.
Is cache busting URLs still valuable? Is there a better way to do that in HTTP2?
I think it is still the caching mechanisms has almost stayed the same. So whatever you did before is definitely a good way of doing it. Talking about e-tags, for example, or just putting the M-time in the URL. This is all very valid, and due to the fact that we are a lot talking about CDNs and stuff, I think it's maybe even more important, but this depends on your setup. But this is not something the protocol takes away from you. It just offers the same mechanism which has been around before, like cache control headers and stuff.
I was just wondering if there's a way to do it with server push. I thought that could be interesting, but if people aren't using it anyway.
This depends how you implement it, right? I mean, you can upgrade an asset which is in the browser cache, and if you it's just doing the lookup by path, right? So if you have the M-time in the actual path, upgrading doesn't it is a different asset for the browser, right? Even though it's just changed a little bit. So then upgrading it with server push doesn't make a lot of sense. If you don't have that and you have e-tags, server push could help you here. But
Thank you.
You're welcome. Okay, that's it. Thank you very much.